The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI Conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI Conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Okay. Next up was a presentation that was prepared by Ryan Dasko of BASF, but unfortunately he couldn't make it. Luckily we have Brad Violetta willing to give that presentation. So please welcome Brad Violetta of BASF.
Thank you, Dave. So I'm thank you. I'm chairman of 212, and I'm the co-moderator of this session. So it's automatically my role to fill in for any speakers that don't show up. So I will attempt to give this presentation justice. And it's sort of interesting that the title of our session is about innovation in chemical admixtures for sustainability. And look at the title of my presentation. It's Hydration Controlling Admixture Technologies Provide Sustainable Concrete Performance for 25 years. So, what's old is new. And, I think you've all probably heard about hydration controlling admixtures. There's several of them on the market. There have been for a lot of years, and they're being used for a lot of different applications. But they're really coming into their own right now, especially due to the sustainability movement. So I'd like to talk about that a little bit. The presentation today will address some of the industry challenges, a little bit about hydration controlling admixtures, why are they sustainable technologies, some applications, financial and environmental impact examples, and then some calculators to determine those, and then a couple of takeaway messages. And so one of the issues facing our concrete industry today is that somewhere around 2 to 4% of all concrete produced is returned to the ready-mix plant. And that could be for a lot of reasons. It could be rejected, or because it was over-ordered, or they ran out of time, or temperature. There's a lot of reasons why concrete gets rejected, but 2 to 4% is a lot. In 2011, concrete production in the United States, ready-mix, was about 263 million cubic yards. So if you just said 5% of that, that's 13 million cubic yards of concrete that's coming back to our plants. And I want to tell you something. In that 2011 number of 263 million cubic yards is very depressed, right? In 2007, 2008, before the recession hit, that number was up to 460 million cubic yards. So you can take this number and double it almost. And so, this is a lot of material that's going to waste. And financially, from a ready-mix plant, typically, these are all numbers from the National Ready-Mix Concrete Association. Typically, for every plant, there's roughly 40,000 cubic yards of concrete produced at that plant. So each one of these plants could have as many as 1,900 cubic yards of concrete coming back that they need to deal with. So not only is there the waste of the materials that are being used to produce that concrete, in this case, average of $53 per yard, times that 38,000 cubic yards, it's like $100,000 worth of materials being wasted. But also, that concrete has to go somewhere. The returned concrete gets reused, or it gets landfilled, and so the producer needs to, of course, deal with that. The other industry challenge is wash water. So at the end of the day, when a truck it needs to be washed out, there's as many as 225 gallons of water that are used to clean the drum, and That water either hopefully finds its way into a recycling system, or in the olden days, it could actually, hopefully not these days, it finds its way into a pond on the plant. And so, again, that's a lot of water and residual material that's going to waste. So, I mean, the math of it is if you have, a plant has 10 trucks and so many 240 working days, there's a disposal of, 540,000 gallons of wash water that they have to deal with, and also the residual waste that's in the wash water. So that's the whole, idea of having to deal with that issue. And so, again, the author goes through the analysis that, if you start looking at that solid waste, it's the equivalent of batching 360 cubic yards of fresh concrete. Remember from before, $53 per cubic yard. So it's a material cost of $19,000 annually, but also the wash water and solid waste is a recycling opportunity. I think if you attend a lot of these sessions, you hear the word hydration controlling admixture a lot. You hear a lot about it because it finds its way into so many different applications. So it was originally developed in the mid-'80s, so that's why the author was mentioning it's having some birthdays. It was actually a concrete producer's idea that said, how can the industry help me, the chemical industry, help me get rid of some of this returned concrete or reuse it. And it basically stops the hydration of cement until, whether it's in concrete or whether it's in wash water, until it needs to be and can be used again. And so it's over those years, it's morphed itself into a lot of different applications. I don't know if you were at this morning's session, they were talking about even in some of these big structures like the World Trade Center, and in different types of concrete, hydration controlling admixtures are finding their way into those because it stops the hydration of these high performance mixes during delivery. But the primary original use for them was to stabilize this returned concrete. So the concrete comes back to the plant, it gets chemically stabilized, and then gets either used again either that day or even as much as the next day. It gets reused, usually in lower specified concrete. Also, the stabilization of wash water, that you can take the wash water at the end of the day, wash your drum out, leave it in the drum if you want, treat it with a hydration controlling admixture, and then batch on top of it the next day, and just cut back on the amount of water you would have batched to compensate for the wash water. Where it started to find its way into other applications, again, is long haul, for delivering concrete very long distances, and then for controlling the setting time of some of these specialty situations, like if there are truck breakdowns or job delays. There's some hydration control impervious concrete to keep it from setting up during delivery. And even in some of these high early strength mixes, they're stopping the hydration during delivery and then hitting it with an accelerator. Happy 25 years old, hydration controlling admixtures. So let's talk a little bit more about this and talk about why these technologies really are sustainable. And like Ketan was talking about in his presentation this morning, just before me, and then some of the other presentations this morning, you're going to see a lot more emphasis in the future about quantifying sustainability. And Ketan talked about, a life cycle analysis, and, we want to be able to quantify, we just don't want to be saying, oh, it's green. I mean, they may be intuitively green, but we want to make sure that we can quantify it. So there's returned concrete waste, there's water needed to clean trucks, and wash water waste. And so there's calculators again to quantify these. And as Ketan talked about, there's different protocols and there's different programs out there to measure the environmental impact, and using the strategic life cycle analysis to compare in this case, both the ecological and the economic efficiencies of alternatives. So it could be on a product like concrete, it could be on a process, making an admixture, or it can be on a technology like some of our other concretes. And so, there's different ways to evaluate them. There's different protocols. ISO has a protocol, and as Ketan said, you can look at from cradle to gate, cradle to grave, even cradle to cradle. But it's acceptable when you're doing that to take into account the three main pillars of sustainability, which is environmental, economics, and then the social responsibility. Sometimes we want to do things because it's just the right social reason to do it. The author will talk about measurements of environmental impact, and the eco-efficiency analysis that he's using measures 6 different environmental impact areas. And typically, when we hear about environmental impact, we hear 2 things. We hear about embodied energy, and we hear about CO2 emissions. And these new protocols are measuring so much more than just that. In this case, again, 6 different impact areas, with the first one being consumption of energy, and the second one being emissions, but much further than just CO2 emissions. There's air emissions, water emissions, solid emissions, and then under the air emissions, there's 4 different categories: global warming potential, ozone depletion potential, photochemical ozone creation potential, and acidification potential. And so, it's a very rigorous investigation. Also, toxicity potential, which is the effect on human health. Do any of these products or systems hurt our community or our people? Then risk potential. Is there beyond toxicity, is there any physical hazard? Is the mining and developing and creating these products high risk physically from accidents or from disease? That can be measured. And then consumption of raw materials. Are the materials being used renewable, or are they not renewable? And finally, land use. In the production and transportation of the materials, are we doing damage to our land? I mean, and it takes into account, is it renewable land? Is it something, example I used this morning was like a Brazilian rainforest or not? And so these eco-efficiency analysis can measure in all of these categories. This one, the protocol that's followed is an NSF protocol. And so in the case of this author is using an eco-efficiency analysis to evaluate the hydration controlling admixtures, and this is a cradle-to-gate analysis, so it considers all of the ingredients from the time they are mined, and it doesn't matter whether it's cement, aggregates, admixtures, water, recycled materials, how the materials are acquired, and then how they are transported, and how they affect the mix design. So, but because it's cradle to gate, it stops at the production of concrete. So it really doesn't matter. It assumes everything else is the same, that the concrete plant are the same, and that the delivery vehicles are all the same. And so it stops at the production of concrete. Some of the analysis that the author does is, first of all, same-day concrete stabilization. So this is where hydration control technology, stops the hydration for 30 minutes to 4 hours, and then fresh concrete is batched on top of it, and then it is delivered in non-critical project applications. So again, the eco-efficiency analysis can measure both the economic as well as the ecological impact of a system. And so in this case, the financial impact was that, again, some of this math you saw earlier, that returned concrete, if you recall from earlier, was the 38,000 yards of concrete at 50,000 was a material cost of $100,000. And then the producer in this example is able to treat that material with $7,000 worth of hydration controlling admixtures and then reuse the concrete at an actual savings of almost $93,000. But if you look at the environmental impact, there's the ability to reuse this material. And so if you do a life cycle analysis of this material in the same day stabilization, you show the environmental savings as opposed to the economical savings. And the eco-efficiency analysis that the author is using does both a quantitative measurement as well as a practical equivalent. What I mean by that is that, for instance, they'll say, well, it's this many kilowatts. It'll do a direct quantification, X amount of kilowatts of savings, and then they'll compare it to something practical that maybe means more to us. So, for example, in this case, the author is saying that in this example of reusing these 40,000 cubic yards of concrete, that there's an environmental impact savings of 1.2 million kilowatts that we're, because we're reusing the concrete. And don't forget, it's measuring the concrete all the way back to the mining of its ingredients. So in this case, 1.2 million kilowatts of energy savings is the equivalent of powering 108 U.S. houses for a year. So it kind of gives a practical idea of how much the annual savings are. And then two other measurements are CO2. And so in this case, it's by reusing this material, instead of producing it fresh and new, it's 1.1 pounds of CO2 equivalent, which is the same amount of CO2s from 61,000 CO2 emissions from 61,000 gallons of gasoline. And the same as the amount of waste that is created by 33,000 people. So the author's point is that there's an economical savings for reusing stabilized concrete, as well as a measured and quantified environmental savings. So with concrete washwater, it's the same, theoretically, the similar concept, in that in this case the hydration control and admixture, the water comes back at the end of the day. They wash out the truck, they keep the water in the truck, it's reused as part of the mixed water the next day, and the producer saves on, there's an ecological and an economical impact in doing this, a positive one. And so again, the numbers that I showed you earlier were the 10 trucks and the 225 gallons. So a material cost to the producer of $19,000. It would cost him about $8,000 to treat all those, and then savings of about $10,000. And then through the eco-efficiency analysis, again, an environmental impact is calculated, and in this case, using 10 trucks, the same 10 trucks, 540,000 gallons of water, and then there's 720 tons of waste in the wash water, that they're able to do a calculation that this is the annual water savings. In this case, is the amount of savings of washing out, 1,867 truck drums. It's the equivalent. Here's the practical equivalent. It's the equivalent of taking almost 38,000 showers. So if you get an idea how much water we're saving, or it's almost the same equivalent of 3.6 million half-liter bottles of drinking water. And that the other applications, for instance, long haul, in this case, where they can extend the delivery time up to 3 to 10 hours, and here you can see some trucks traveling through the Mojave Desert or something. And, so you can go into, the concrete producer can travel into much wider zones. And he can increase his position by expanding his market delivery zone, and then save on any labor and material costs for constructing portable plants that they might have to do as an alternative. And then again, as I said earlier, that some of the additional applications for hydration controlling admixtures include extended concrete set for a few minutes or a few hours on a given project. It helps keep the ambient temperatures down. If there's any truck breakdowns, you can save the concrete. It's used in all kinds of high-performance concretes. You hear about it all the time, the hydration controlling admixtures. Again, I said earlier, they use it in pervious concrete because the pervious concrete is such a stiff mix that upon delivery it would actually start to hydrate. So you stop the hydration upon delivery, and then it's, once it gets delivered, it starts setting up as normal. There's also, it's also used in applications, for instance, when they're pumping concrete long distances underground for mines, for instance. You stop the hydration, because the last thing you want is for the concrete, to set up in a pipeline in a mining situation. And then there's a whole technology about really high early strength concrete, and if you want to learn more about it, you can read our new ACI 212 committee document on state of the art, and we have a whole new chapter on that. But the concept of that is that there's very high early strength concretes being made, usually used for full depth repair applications of highways. So example, in about a 24-hour time period, you can come in, remove a highway panel, do a full depth repair. With normal concrete, you can get up to, even more than about 4,000 PSI in about 4 hours, and that allows them to reopen traffic the next morning. And the reason I'm even talking about that is because it's such a low water cement ratio, high cementitious mix that a hydration controlling admixture is actually used in that to keep it from setting up during delivery, and then it's accelerated at the job site. The example of some of the calculations, again, part of it's economic and part of it's environmental. So if you go through those examples that we just talked about, you can do an analysis of the annual cost savings, whether it's based on truck washout time, labor costs, amount of water, and a whole list of things that you can compare when comparing conventional concrete to hydration controlling admixtures. And so there's tools to do those calculations. There's also tools to then these eco-efficiency analysis to do overall calculations of what's the total environmental impact of these type of systems. And so in this case, what you're seeing is, and I don't know if these are hard for you to read, but these are some of the actual outputs of the example that we showed, where you can, in these examples where you can take all of these and sum them up, and you can do an annual savings of some of these different 6 impact areas I was telling you earlier about. And you can see that there's quite a long list here. And it was similar to what Caitlin was talking about earlier. Energy, this is raw material use, this is fossil fuel consumption, this is global warming potential, this is that photochemical ozone creation potential, which is smog, and then there's acidification potential, which is acid rain, water emissions, solid waste, and land use. And you can see that in these examples that the author went through earlier, that these become very large numbers. Some of them we've already talked about, but you can also see the POCP and the AP and water emissions, and then again take it back and say, okay, what's the practical equivalence of these? And you can see that's all listed here. So again, it talks about the environmental impact statement, talks about both the ecological and the economical impact. So the takeaway messages from the author are that hydration controlling admixtures control cement hydration that allows the recycling of concrete and wash water. He says there's 7 applications for concrete producers that we've talked about. There's 25 years of industry experience, so that it's a very used material and understood material. That there are calculators that can determine the economic and sustainability impact of these type of materials, and that these are materials that help concrete producers manage their concrete and wash water waste streams and increase plant operational efficiencies. So that's it. Do you have any questions?
No, in one of the slides you have the 400 psi. I think you say 4,000 psi.
Oh, I'm sorry.
Okay, but what about rinkage? Do you have some problem with rinkage or cracking in this slab because of the really very, very high early strength?
Yeah, yes. So good question, and thank you for correcting me. I did say 4,000. I meant 400 psi flexure in 4 hours.
Okay.
And there's been a lot of analysis on this type of concrete, both from strength development, durability, and shrinkage. And the shrinkage is fairly low because it's not really high amounts of cementitious as much as it is really low water cement.
And you have very low water. And you have very low water content.
Very low water. And I hate to be a walking advertisement, but in our new ACI 212 document, we have a chapter on those type of concretes with a lot of good references.
Very good. Okay, thank you.
I don't know if anybody in ACI is working on it, but I think the calculator you need is the one that calculates the right amount of concrete to order, because then you'd save all of this.
Good point. Good point well taken.
Thank you.